Right. Welcome back, everyone. Thank you for your patience on having to miss Monday's class due to unavoidable circumstances. I had to cancel my Monday and Tuesday classes, as you saw in your email. I had said that all due dates would be unaffected by that. What I really meant was homework due dates. Our test was originally going to be, this is not our class, I have to save that later. Our test dates were originally going to be the 12th and the 13th because we were supposed to finish on Monday the 5th, and then I said I like the test to be a week later. Well, we didn't finish 5.8 on Monday the 5th because we didn't have class. That means we're going to be doing and finishing it today the 7th, which means our test will be a week from today, which is the 14th and the 15th. So we're just going to edit that. It just gives you 2 extra days in time until it happens. I still don't know how many questions it's going to be. You are going to have 90 minutes. So I had said that I was going to do this test in my math lab, and it would be under your quiz and test section. I might go back on this. I might go back on this. I probably won't, but I might. I might make this just a handwritten test. I have not fully decided because I'm thinking about some complications that you don't need to worry about. But yeah, the idea that it'll be in my math lab, I'm going to say 75% certainty right now, but there's a 25% chance. I'm just going to give you a handwritten test like I would normally do in class for this one. But don't hold me to that yet, so this little bit just might change a little bit. But it will still be a 90-minute test. You'll have to submit your work within 15 minutes of finishing the test if it's in my math lab. If it's just a paper pencil test, then you submit it to me by 11:59 on the 15th. That is no longer a question mark. Ballpark 25 questions, some extremely short, some a little on the longer side of things, as we've seen with the examples we've done. I mean, sine of 30 degrees, you can answer like that. Cosine of 45 degrees, you can answer like that. Cosine of pi over 4, you can answer like that. It was the same question, in fact, that I just asked. Please understand, and I mentioned this at the very beginning of the semester, I am not going to give you any problems on a test ever that are convert degrees to radians. I'm not saying you won't have to do that for some reason. What I'm saying is I will not give you a problem where the only thing you have to do is convert degrees to radians or vice versa. So if I give you the sine of pi over 6 and your answer is 30 degrees, no, absolutely wrong. Okay, 30 degrees is pi over 6 converted to degrees from radians, but you still have not answered the question I asked. All you've done is asked it in a different way and misconstrued it as saying that 30 degrees was the answer, but no, that's saying sine of pi over 6 would be the same thing as sine of 30 degrees. So my students who generally don't practice the homework and don't do anything, those are the ones who tend to do what I just said, and then they miss half the questions on a test, and that's barely an exaggeration. Maybe a third of them. So please understand, there will never, ever, ever, ever be a question where I'm just saying take the degrees and convert it to radians or vice versa. You may have to convert your radians to degrees to better understand the angle, or for some reason vice versa, but that's not the problem. You have got to know, remember, you're supposed to have, this is a no notes, no books, no extra information test. So you're supposed to not have any of this written down, start your test, and then you could write it down from memory, not from a piece of paper in front of you. So all semester long, every single one of these things will continue to test us. It will never go away while we are doing trigonometry. You will constantly need to know SOHCAHTOA. You're constantly going to need to know your reciprocal functions and your tangent and cotangent, being sine over cosine or vice versa. You're constantly going to need to know your Pythagorean identities. You're constantly going to need to know these 2 right triangles, the unit circle and its 4 quadrilateral points, the fact that sine goes like y, cosine is the x, tangent the ratio. A smart trig class to get the signs, the plus or minus signs of your trig functions in different quadrants if you're not just dealing with right triangle trigonometry. All right, so let's pick up where we left off. and 5.8, which is applications. Just make that title just a little bigger. There we go. All right, so I just want to make a couple statements about the inverse trig functions before you actually get in the applications, and that is because there might be a time with an application problem where you need to know these facts. So as a reminder, these are reminders. If you have y equals sine of theta, that's the same thing as saying theta is equal to the inverse sine of y. But your theta must be between negative pi over 2 and pi over 2. Then we said if you have y equals cosine of theta, that means it's the same thing as saying theta equals the inverse cosine of y. But with inverse cosine functions, the theta must be between 0 and pi. And then we had if y equals tangent of theta, then theta is the inverse tangent of y. Where your angle is like sine, it must be between negative pi over 2 and pi over 2. So maybe when you're doing an application problem, you get this equation y equals, or maybe you have a number over here, it's 13 equals sine of theta. And you're supposed to be finding the angle. Well, you can find the angle by doing the inverse sine. But you have to make sure that your application problem, if your angle was in quadrant 2, for instance, and you're doing an inverse sine, it's going to spit out, your calculator is going to spit out an answer that's not in quadrant 2, it's going to be in quadrant 1, so you would have to know to transpose that angle to quadrant 1. So again, these ideas are important for applications where you have the sine of the angle, cosine of the angle, or tangent of angle equal to that ratio. So you know you have to do that the angle is the inverse trig function, but you also have to know where those angles are valid, because your calculator is going to only give you answers in these windows. However, for an application, your angle could have certainly been in one of the other two quadrants. The inverse trig function isn't valid, so you have to use the answer from your calculator as a reference angle and then put it in the correct quadrant. So you might have an angle that's supposed to be in quadrant 2, you use an inverse sine, and the calculator says, oh, it's in quadrant 1. But you know, well, no, I know when I drew up the picture, the angle was in quadrant 2, so I have to use what my calculator told me as a reference angle. This is when things get really complicated. I will mention that the applications we're going to be doing together, this won't even be valid. So this memo at the bottom, which I'll just type up, right triangle. Why is my font still so small? Problems. The angle and its quadrants aren't an issue, because quadrant 1 is always valid in the inverse trig functions. There we go, a little better. All right, so let's just get down to brass tacks. Example 1. Complete triangle. I'm going to give you a right triangle. And I'm going to tell you that this angle right here is 34.5 degrees. I'm going to tell you that this distance right here is 125. I'm sorry, that's not right. I'm looking at a later example. The 34.5 is right though. It's 10.5. And that's it. That's all I'm giving you. So I'm asking you to complete the triangle. So what I'm asking you for is, well, if I want to label all the sides, let's label this as angle A. We'll call this angle C. I wish I had put my triangle a little, shoot. We'll do it this way. Copy, paste. There we go, there we go, there we go. And then I'm going to call this angle B. So we tend to use capital letters for angles. So this is a capital C, this is a capital C. We tend to use lowercase letters for side lengths. So uppercase letters for angles, lowercase letters for sides. Now I labeled this as angle A, and you can see it's 34.5. So I'll call the C the hypotenuse per usual. So this is going to be a lowercase c. Maybe I'll even make that other one a much more exaggerated C. Please, thank you. And then the legs would be your A and your B. It doesn't matter which one you call which normally, but since I called this angle A, in trigonometry, we have to make these the same, so the side opposite has to be the lowercase a. So again, because I made this an uppercase A here, the side opposite of it has to be the lowercase. Because I made this an uppercase B, the side opposite where the 10.5 is has to be the lowercase b. Because this was angle C, which is 90 degrees, this has to be the lowercase c. So we know angle A, we know angle C, but not angle B. We know side length B, but not A and C. So there are three things we have, and there are three things that are missing. This is a pretty common triangle problem. And we are going to keep doing this type of problem as the semester progresses, but in more complicated ways. Right now, we are basing everything off the fact that we have to have a right angle. Eventually, we won't. And that's going to be awesome, but it complicates things. All right, well, the easiest thing to find first would be angle B. Angle B, well, we know that the sum of the interior angles of a triangle is 180 degrees. So angle B should be 180 minus the other two. Should be 180 degrees minus angle A minus angle C, which is 180 degrees minus angle A was the 34.5 degrees, and then angle C was the right angle of 90 degrees. And when you do that subtraction, you will get 55.5 degrees. So that's angle B. Now we have all three of the angles. That's the easiest thing to do. When you know two of the angles, the third one just falls in place because we know the sum of the interior angles of a triangle is 180 degrees. If you don't know that, you were just retaught it. And please don't ever forget it again. All right, so we got B, so that one's done. The only thing we're left to find now are these lengths A and C. And you might go, oh, Pythagorean. Well, Pythagorean, the a squared plus b squared equals c squared only works if you know two of the three. All we know so far is one of them. So Pythagorean's not going to work yet. We can certainly use it later, and we might. But for now, what we got to think about is, all right, we know these two angles, and we know this length. We can choose to find A first, or we can choose to find C first. No one cares. I'm going to choose to find A first. So I'm going to go after A first. And I can't just say A equals blah, blah, blah. We're going to have to do some trigonometry and some algebra. So the basic idea, and this was something we also reiterated at the very end of last class a week ago, is as long as you know two of three things, you can find the third thing. So we have an angle, and let's just go with the angle A since B is one we found. So we know 34.5 degrees. We have its adjacent side, and we want to know its opposite side. So we've got to think about what trig function uses an angle, the opposite, and the adjacent. Well, tangent and cotangent. But don't use cotangent, use tangent because it's easier. All right, so we will say that the tangent, and I'm talking about this one, so the A is the opposite, the B is the adjacent. You could still use angle B of 55.5 degrees, everything's just upside down. So the tangent of 34.5 degrees would be its opposite of A over its adjacent of B, but we know B is 10.5. Well, All you do is multiply both sides of this by 10.5 to solve for a. So we take 10.5 times the left side and 10.5 times the right side. Sorry, I got to squeeze that in a little bit. We do that so that the denominator clears. So now this just says that 10.5 times the tangent of 34.5 degrees is equal to a, which we can just put this in a calculator. Now, I usually give a no calculator test for test 1. And so far that is still true. If I give an application where I feel like the calculator is necessary, I'll let you know ahead of time, hey, for one question, for the word problem, you'll need to pull out a calculator. So once I create the test by next class on Monday, you'll have that information, but I still have to build the test. The events of, well, it was pretty much an all weekend thing, and Monday and Tuesday have kept me insanely busy, so I haven't made our test yet. So yeah, calculator, that's all we're doing. Pull out a calculator. If this was a no calculator test, this would be the answer. And I would probably have to go and input your points for that manually, which wouldn't be a problem since there's only 10 students. All right, so we just do everything first, right? Nope, we check our mode. And I'm in radians, where I'm gonna be typing in degrees, so that's a problem. So we gotta switch our mode to degrees. Get out of that menu with second quit, and just type 10.5 times the tangent. You can hit times if you feel like you need to, but for my calculator, I don't. And then 34.5 degrees, close our parentheses. And we end up with 7.2 blah, blah, blah. I did not say to round to 1 decimal, but that's what we're gonna round. So we're just gonna say this is 7.2. So that's this length. We now know the 2 legs, which means we can find the third side by Pythagorean. Alternatively, if you wanted to use another trig function, what you could do is say, all right, well, we know the angle, we know the adjacent side, we now also know the opposite side, so we could find the hypotenuse by using the sine or the cosine function. If you use cosine, you'd be going with the adjacent, which is the 10.5, so you'd go 10.5 over c equals sine of 34.5, or if you wanted to do, I think I said sine, I'm going to say cosine, 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 cosine. Or if you wanted to use this information from A, you'd say the sine of the angle is A over C. And then you would do pretty much the same thing we just did in the last one. But most people, once they can do Pythagorean, they go ahead to Pythagorean. So let's use A squared plus B squared equals C squared to get the C now. So we know that 10.5 squared plus 7.2 squared would be equal to c squared. Just take the square root of both sides, so that says that c is equal to the square root of 10.5 squared plus 7.2 squared, which if you plug that in a calculator, big square root, 10.5 squared plus 7.2 squared, parentheses, and we get 12.7 when we round to 1 decimal. So there are our 3 unknowns. We found the missing angle of capital B, and we found the leg and hypotenuse, what we called A and C. What you call these letters is completely arbitrary unless the example in my math lab already defines them, and then you got to make sure you're putting them in the correct spots. All right, let's try another. Example 2, same thing. We're going to complete the triangle. Actually, no, we're not going to complete the triangle. We are just going to find the important bit of information. So I'm going to make another right triangle. These are not being drawn to scale. Please don't think that they are. We're going to have this be 57.2 degrees. We know the horizontal distance, we saw this number earlier, 125. And I want to know, what is the height here? So that distance is what I'm going to call A. I don't want to know the hypotenuse. I don't want to know the other angle. I'm the boss. I ask you, the employee, to go out and you stand 125 feet away from a building. You get your electronic device to be able to measure that from your position on the ground to the top of the building, it's 57.2 degrees. And I'm asking you to confirm the height of the building. Maybe one contractor said it was this height. Maybe one contractor said it's 200 feet tall. Maybe another contractor said it's 194 feet tall. And I'm asking you, well, which one was right? Who did the wrong math? Who do I got to fire, or who do I not want to rehire? You know, that kind of thing. So you stood 125 feet, away from the building. You got your electronic device that measured 57.2 degrees to the top, and you're going to confirm the height with very basic trigonometry. So you have your angle, you have the adjacent side, and you're wondering what the opposite side is. So you ask yourself, well, self, what trig function uses opposite and adjacent? Well, we just said it last time, tangent. So we're going to say that the tangent of 57.2 degrees is equal to its opposite over its adjacent. Its opposite we've called A. Its adjacent was given to us as 125. You're going to multiply both sides by 125. To isolate the variable. So the 125 is on the right, cancel. If your variable's in the bottom, you'd be multiplying both sides by the variable. You got to get rid of the fraction part. And what this tells us is that 125 times the tangent of 57.2 degrees is equal to A, which we can just stuff in a calculator if we need the approximation to one decimal place. So 125 times the tangent of 57.2. I already put myself in degrees earlier, so I know I'm still in degrees. I trust myself. And we get 193.96 blah, 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 which rounded to the nearest tenth would take the sixths to round up, so that 9 becomes a 10. So even rounding to the nearest tenth, we round this to 194. So I gave you two options earlier. I said contractor A said it's 200, contractor B said it's 194. So contractor A is fired because he was wrong. Maybe not fired, maybe scrutinized more, I don't know, but you get what I'm saying, I hope. Now, a similar example, let's say you were more interested in this angle, kind of like that physical therapy problem I did at the end of last week. So maybe you have the problem this way. Maybe you know this distance is 125 feet. Maybe you know this distance is 194 feet, and you don't trust your measuring device, and you're wondering what this angle theta is. So maybe your measuring device said it was 57.2, and maybe Bob's measuring device said it was 56.9, and you're wondering which one is more accurate. So you'd go, okay, which trig function uses opposite and adjacent? Well, it's still tangent. So you'd say the tangent of your angle is equal to 194 over 125. And this type of problem is what I was referring to at the very beginning. We have a tangent of an angle equals some number, but the thing we need to know is the angle. It's not solved for here, so we have to do this instead. And we don't know any particular right triangles where this would be a known angle. So what we do is we turn this into theta equals the inverse tangent of 194 over 125. So we pull out our calculator. Now this was a right triangle problem. All our angles are from 0 to 90. So all of that, it's between this angle and that angle will be irrelevant for us. It's easier. So we just do second tangent. 194 divided by 125. Close it, see what we get. And we get 57.2. So the other person's measuring device that said 56.9 is now going to be calibrated or maybe just thrown in the trash. So theta is 57.2. And that's degrees. We made sure we were in mode. These problems where we might have to worry about the angle, again, you might have one, I think one in the homework, and that's it. I'm not going to do that on the test, though. Yeah. Okay. That was example 2, even with a extra little sidebar. I just want to write here similar but different. because this was me giving you a different value. Instead of giving you the angle and a side, I gave you two sides. That's how you would have to find the angle. If I gave you the opposite and the hypotenuse, you'd want to use inverse sine. If I gave you the adjacent and the hypotenuse, you'd want to use inverse cosine. How do you know? Because that's what those trig functions deal with. SOHCAHTOA, SOHCAHTOA, SOHCAHTOA. All right, example 3. In this example 3, we are going to see text example 4. So I'm actually going to pull up the textbook. I also want to pull up another blank file so I don't show too much stuff. I don't want to give you all the work and the answers and stuff. So I got my textbook loaded, hopefully still. Yes, I do. And then we'll do this. There we go. Do I need to scroll down just a touch? No, that was good enough. Don't look, don't look, don't look. Close your eyes. Okay, you can open your eyes. All right, so example 4, you are taking your first hot air balloon ride. Very awesome. Always do that at least once unless you're terrified of heights, in which case you do you. Your friend is standing on level ground 100 feet away from your point of launch. So you can see the diagram to the left. We got our hot air balloon here, and then the basket's on the ground initially. And the balloon would be on the ground initially too before it fills up with air, but you know, we don't need to get too crazy with this. So your friend's standing 100 feet away. So 100 feet away from where you were standing in the basket when you first started the launching process. And he's making a video of the terrified look on your rapidly ascending faces. Don't you love that? How rapidly though? How rapidly are you ascending? So we're not going to treat this as a calculus problem, but we're kind of setting it up as one. At one instant, the angle of elevation from the video camera to your face is 31.7 degrees. So here's your friend, and his eye was level to your eye. You're the same height. And where he's holding the video camera, the angle up to your eye in there, we're kind of like neglecting the fact that we're about 6 feet tall. We're just saying there's 6 feet of spacing here, but they're on both sides, so it's irrelevant. So originally, when you start going up, the angle is 31.7 degrees, and you've got some height A. Then a minute later, so you apply your hot air. It fills up with more hotter air, and it causes it to rise due to pressure in heat, and all that stuff being an inverse relationship. Blah blah blah. Anyways, so a minute later, now you're way up here, and the angle that the camera that you can measure is 76.2 degrees. So at maybe 2 minutes in, 31.7 degrees, and then 3 minutes in, which is 1 minute later, it's 76.2 degrees. So we picked up speed. It's very clear that we picked up speed. So they want to know, how far did you travel to the nearest tenth of a foot during that minute? During that minute. So they are saying they want to know, all right, at the start of that 1 minute, you're here. At the end of that 1 minute, you're here. They want to know, what is this height? And I'm going to call it X. Now, that is not the entire length of that larger triangle. It's not the length of the shorter triangle either. That length is the difference of those two things. So what we're going to have to do is find A first, then find B. I think we can actually find them interchangeably. And I know we can, but we'll do the smaller than the bigger one. So we'll find A, we'll find B, and then we'll just say that X is the difference of B and A. That's a very basic concept. If this length, if the total thing is B, if A makes up this portion, X would be the difference of the two things. Because A plus X is B, that means B minus X is A, or B minus A is X, either way you like to do it. So that's going to be important issue 1 with this problem. So I'm going to redraw this triangle. Then I'm also going to draw them as their own triangles. And let me clear my screen, come off of annotate. And let's pull up our actual, okay. So we had big picture, and then we had a smaller triangle inside of it. So for the smaller one, this was, I believe, 31.7 degrees, if I wrote everything down right. And then for the larger one, it was 76.2 degrees. Oh, I forgot to do this. That's the 31.7, and it's going to look a little exaggerated, but this is the 76.2 degrees. Now we had the height, and we didn't say exactly how long our flight was at this point. We had some height, maybe 5 minutes in, maybe 10 minutes in, I don't know. So A would be the height there, and then B, we said, was the height of the entire thing. B was going from here to here, and then we called X the distance from here to here. That's what we actually want to find, X being the difference of B and A. This is a lot of information all at once. Here's my first suggestion. Draw these as separate triangles. So let's make 2 triangles. Let's do the blue one by itself. That's terrible looking. Let's try it again. Where this is 31.7 degrees. I also forgot to write the 100 feet on the bottom. That was the horizontal distance. So this is still 100. And then this would be A. And then for the bigger triangle, I'll do in red. I'll do red for the bigger triangle. So that was a larger angle. I'll try and make that visible. That was 76.2 degrees. This was still 100 though, and we called this distance B. So what we got to do is we got to find A from the blue triangle. We got to find B from the red triangle. And then our number is actually just the difference of those two things. So for the blue one, all right, we got an opposite and an adjacent. We don't actually have the opposite, but that's what we need. So angle, opposite, adjacent, we're going to use tangent again. The tangent of 31.7 degrees would be equal to the opposite over the adjacent, A over 100. Same thing as before, multiply both sides by 100, you get 100. Tangent of 31.7 degrees equals A, and you can put that in a calculator, which we will do right now. I almost wonder if y'all just heard my stomach growl. I'm very hungry and had to skip lunch because my classes ran over. 100 times the tangent, 31.7. 7, I know I clicked it, here we go. And we're gonna hit enter. And what we come up with is 61.7 blah, blah, blah. Let's keep this to rounding to the nearest tenth, which will be 61.8. So 61.8 is equal to A. And let's put the units as what they should be. We're talking about feet, so it's 61.8 feet would be equal to A. Now let's do the same thing for the red triangle. So A was the height whenever we started the clock, 4 or 5 minutes in. I don't even know. We don't have to worry about that particular detail. B is the height 1 minute after that initial height. So yes, we started on the ground. After maybe 5 minutes, we were 61.8 feet in the air. Then another minute passes. Now we're wondering how high are we now? All right, so opposite, adjacent, it's tangent again. So the tangent of 76.2 degrees is equal to B over 100. So we're going to multiply both sides by 100. That way we can solve. So we have 100 tangent of 76.2 degrees is equal to B. Then we're going to stuff that in our calculators, which, come on, pull up. So we'll do 100 tangent of 76.2. We'll close it for good measure. And we get 407.1 feet, 407.1. So 407.1 feet. That is how high we were after that 1 more minute. Man, we managed to fly quite a distance in that 1 minute. So maybe we weren't 61.8 feet in the air 5 minutes in, maybe that was 5 seconds in. Well, if you actually knew how hot air balloons kind of ascend, they do ascend very slowly at first and then quicker and quicker. So this could have been 5 minutes in and then, all right, we've picked up speed. Okay, so what was the point of this? We wanted to know what was the distance we traveled in that 1 minute, which was the difference of those B's and A's. So X would be B minus A, which we said is the 407.1 feet minus the 61.8 feet. And when you do that, what is that, 345.3? Yes, it is, 345.3 feet. That is how far that hot air balloon traveled in 1 minute. This is one of my favorite types of problems. I love this problem because it makes you think big picture. You've got a small picture to worry about, small picture to worry about, then big picture. You have a calculation to do outside of just doing trigonometry on 1 or 2 triangles. You have to think about everything. You have to put the pieces of the puzzle together. All right. So with that being said, do I want to do... I got one more example. Well, 2 more actually. I need bearings for it anyways. Okay. I was thinking if I wanted to do bearings last, but I did give an example that uses it, so I need to describe it. All right. Bearings, small font again. So in this course, we have said that you always measure your angle for traditional angles from the positive x-axis. If we're doing a reference angle, either the positive or the negative x-axis, but never the y-axis. Bearings are the opposite of that. Bearings feel like you're measuring from the y-axis, or either positive or negative. So the way this works is, start in the first direction, C. Move X number of degrees towards the other direction described. A bearing is something like, I don't know, north 50 degrees east or south 14 degrees west. That's a bearing. So bearings are very often used for ships, for sailing. So because you're just thinking about, all right, well, I'm going based off of north or based off of south. So they call it a north-south bearing, and that's actually one of the homework questions. I'm just spoiling that. It's one drop-down menu is north, one south, that's it. So bearings are measured north-south. So it goes north, then an angle, and then east, or south, and then an angle, and east or west. So when they say that bearings are measured from on north-south, they're saying that you start that whole phrase with north or south. And then the second part is either east or west. What exactly am I talking about in case that was too much? Example, what are we up to? 4. Draw angle described. A, weird when it does that to me, but whatever. We're gonna have north 18 degrees west. So I want you to draw this angle. Well, I hope you all know that north would be here, east would be here, south would be here, and west would be here. Instead of just x and y, these are no longer x, y axes. These are north, south, east, west, weather vane kind of things. So we're supposed to be drawing the angle north 18 degrees west. So north by 18 west is how some people like to phrase it. North by 18 west. set says we're thinking about, all right, we're heading in a northern direction. So we're either heading northern or south. So we're heading in a northern direction, but then we're going to go 18 degrees towards west. If I said in 18 east, I would go 18 degrees towards the east. So this angle would look something like this, and the 18 degrees is right there. Again, this is absolutely completely different from any way we've measured an angle ever in this course up until now. Bearings are completely different from traditional trigonometric angles. But in the real world, a lot of people talk about bearings, so it's an important thing to discuss. Now, what the homework tends to do is the exact opposite. They tend to show you the angle, but they would give you, all right, they'd say this is, what, 72 degrees? They'd give you the blue and say, what is the bearing? And you'd have to figure out the black ink that I wrote. It's north, 18 west, because you'd have to figure out, well, this is 18, and then that's north and west. But you can do it either way. It's not really a complicated problem. It's just getting used to the notation, that it goes letter, number, letter. And I'll even admit, if I don't do bearings for a year, I always want to go the number and then the two letters. So 18 degrees northwest is the way I think in my head. So again, if I don't do this for a long time, I get the notation wrong. But I also have the ability to look at it once and then remember it for a year, which is what we like. It's okay to forget things as long as you can very, very quickly pick them up again. All right, B, let's do south 81 degrees by west. So we draw this up, east, north, south, west. Crummy looking in. So we're going south by west. So our angle, instead of pointing up, we're going to be pointing it down. So maybe it's here, maybe it's here, maybe it's here, maybe it's here. It's one of those four, basically. But it would not be one of any of these. So we're going south, and then the next letter is west. So we are not going to swing this way. That would be swinging towards east. We're going to swing towards west. And we got to swing 81 degrees, which is quite a bit. So this would be our 81 degree angle, which would make the more normalized trigonometric reference angle of 9 degrees, or the true trigonometric angle of, what's that, 189 degrees. But as a bearing, it's south by 81 west. Or 81 degrees south by west. I mean, I don't care how you say it. Outside of this class, I don't care how you write it. I don't deal with bearings a lot. Which, if I don't teach a trigonometry class for a year, that's the scenario I literally described. A lot of teachers want to make you think that they absolutely know everything and remember it forever. And they're full of something I won't say on a recording. Some of them are geniuses. But most teachers are just adaptable, and they can, you know, not see something for 4 or 5 years, come back to it having forgotten a little bit, but remember what it is, re-pick it up, and still be able to communicate it effectively. All right, so next we're going to do example 6 from the text now that we have bearings in mind. So bear that in mind. I am so sorry for that pun. I'm not actually, but I like to pretend. Example 6, here we go. And again, let's try not to spoil too much of the fun. So let's get our cover up. Here we go. A boat leaves the entrance to a harbor and travels 25 miles on a bearing of north 42 degrees east, or north by east 42 degrees, or north 42 degrees by east, however you want to say that. The figure shows that. So we're on a bearing north 42 east. So here's the harbor entrance, and we're heading out this way. So this is the direction we're initially heading. So this is us initially. So we're going north by east 42 degrees. So it means we're going mostly north, but then swinging 42 degrees towards east, not west. So we go, and then something happens. The captain turns the boat 90 degrees clockwise after a while and travels 18 miles. So we traveled 25 miles where this red ink is that I currently have, and I'm about to put more red down. And then you make a 90-degree turn. So here's our 90-degree turn. And they say we turn clockwise, so that's why we went. So this was where we would have continued going, but then we turn 90 degrees towards clockwise. So that was our turn. If we'd gone counterclockwise, we'd be going in this direction instead. Undo, 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 undo. There we go. Okay. So then we travel 18 miles. Here's our boat now. So you are here. And they even tell us that that bearing was south 48 degrees 18. So here's your north-south line. And on that, we're traveling south, so south, and then but south towards east, so it's pointing that way instead of left. So this was north and east, then south and east. First of all, they want to know how far is the boat to the nearest tenth of a mile from the harbor entrance. So the first thing they want to know is, what is C? What is the hypotenuse of that right triangle? So it's a good thing our captain made a right turn, because otherwise we wouldn't know how to find this yet. We'll need a later chapter for it, but we will get there eventually, of course. So we want to find that distance first. Then the second question is, what is the bearing to the nearest tenth of a degree of the boat from the harbor entrance? So the last thing they're going to want us to know is, what is this angle? So just from the harbor entrance to our current position, what bearing is that? And you can see that it's going to be a northeast bearing, because from here we're going north and east. So those are the two things that we need. Let's see, I'm gonna do this. Let's do, sorry about that extra little scribble there. It's gonna be there for a few minutes. So we said example 5. Let's just see the text, example 6. Let me just, how far is the boat to the nearest tenth of a mile? How far is the boat to the nearest tenth of a mile? So A, how far is the boat from the harbor? Which means we're finding that C over there. So I'm just going to draw up the triangle. So we know this was a right angle. We know this will be the angle we need to find eventually. And we need to find C for now. We know this distance was 25 miles. We know this distance was 18 miles. First thing we're going to do is find C. So C equals, well, that's a right triangle, so A squared plus B squared. 25 squared, sorry, C squared equals 25 squared plus 18 squared. So C would be the square root of that. That's an ugly square, isn't it? Let's try again. There we go. Which one we round to the nearest tenth? Let's pull out our calculator. We're doing big old square root of 25 squared. That was not a square root. Let's start over. Big old square root, 25 squared plus 18 squared. And we get 30.8. Rounded to the nearest tenth, so that'll be 30.8 miles. So yeah, we went 25 miles this way, we went 18 miles that way. So our boat, in terms of fuel consumption and actually how far it traveled, we went 43 miles. We have moved 43 miles. But in terms of from our original position, if you just wanted to take a straight path, so maybe we were broke down and someone's got to scoop us up, then that boat that's got to scoop us up is going to have to travel 30.8 miles. They don't care that we went 25 miles this way and 18 miles that way. They're not going to be putting 43 miles in our boat and traveling the same path. They're just going to say, we know your position. We're heading directly towards you because we're not going to waste fuel. For part B, they wanted to know what was the bearing from the harbor. Now I drew this as a flat. It was a little crooked over here. Don't worry about that. This is good enough for government work, just not drawn a scale. Well, here's our angle. We have the 3 different links here, but we approximated C, so I would try not to use C. So I would say it's probably a good idea to use tangent again. So we'll say that the tangent of our angle is going to be equal to its opposite. Now, this is drawn differently than how we usually draw our triangles, but that's okay. The opposite is the 18, the adjacent is the 25. So we go, tangent of the angle is 18 over 25. But in order to solve for the angle, because it's inside, that means you need to go to the inverse tan function. Now, if this was, a square root of 3/2, or a half, or a square root of 2/2, then you know it's a 30 or 45 or 60 degree angle. But that's not the case here. So theta would be inverse tangent of 18/25. So we'll stuff that in our calculator. Inverse tangent of 18 divided by 25. And we get 35.8 degrees when rounded to the nearest tenth. 35.8 degrees when rounded to the nearest tenth. But is this a bearing? No, that was supposed to be a question mark. It's not. It's not a bearing. That is absolutely not a bearing. That's a traditional angle because that's measured from a horizontal positioning. So what we actually have to find is the bearing. So if we were going, let me put my annotate back on. So this theta we know is 35.8 degrees. The actual angle we are trying to find is this. This is the bearing angle because we got to go from north to east or south to west if that's how it was positioned. So this is just basic arithmetic. We know the angle here was 35.8 degrees. We know this angle is 42 degrees. Well, we swing 42, then we swing 35.8. So that whole angle would actually just be the sum of them. So our angle, oops, let me not do it that way. Come off of annotate, there we go. So our angle would be the 42 degrees plus the 35.8 degrees, which when you add those up, you will get 77.8 degrees. That is not the, if you just wrote this, that would not be it. That's not a bearing. Bearing itself has to throw the north, the south, the east, the west, that stuff into it. So we're going in a north direction, but also an east direction. Don't go east then north. It has to go north, then east with the angle in between. That is the bearing that our rescue ship would have. Humana. What do we got? 15 minutes. Let's do another. Now I don't need the textbook anymore, so I will maximize this. And I need to clear my annotations so that that's not sitting up there. All right. Last example of the section, example 6. You're flying a kite, you know the length, the string, the 80 feet. How do you know? You extended it and you measured it. Friend observes that when taut, not as in teaching, as in a tight string, it forms a 22 degree angle elevation. Angle of elevation is the traditional angle we've been using, not a bearing. And that's when the handle is on the ground. So not from 4 or 5 feet up, however high we're handling it. We're going to put the handle on the ground so we can keep things clear and precise. How high is the kite? So it would be very difficult unless we're flying this kite right next to a building and we put someone in the window and they measure how high up they are, by dropping a measuring tape or something like that. These would be a lot easier things to measure. The 80 feet of string you can do on the ground. The 22 degree angle, you can get a caliper or just any boring device that measures angles. Doesn't even have to be a digital crazy caliper to measure 22 degrees. We didn't go to the nearest 10th or 100 or anything like that. We can just get a protractor. So a picture's worth 1,000 words, right? Let's draw it up. So we're standing here. So we're here on the left. So this is us. This is you, if you will. And then we're flying a kite, and the length of the string is known to be 80 feet. And your friend measures a 22-degree angle. 22 degrees is kind of small, so we'll make this kind of small. So this right here is where the kite is. And this is our 22-degree angle. So we know we're going to have a right angle here if we just drop it directly down. Now we know that the length of string of the kite when fully extended is 80 feet. Is this the 80? No, that's definitely not the kite string. That's the height off the ground. Is this the 80? No, that's the distance from you to directly under the kite, but that's not the string. The string is the hypotenuse of this right triangle. This is the 80 feet. And the thing that we want to know is the height of the kite, which would be this vertical distance right here. You could call it X, you could call it B or A. I'm going to go H for height. All right, so we got a right triangle with an angle, a known hypotenuse, and an unknown opposite. Which trig function uses an opposite and a hypotenuse? The sine. So we'll say the sine of 22 degrees is equal to its opposite of H over its hypotenuse of 80 feet. You're going to multiply both sides by 80 to clear the denominator. So you get 80 times the sine of 22 degrees is equal to H, which we can stuff in a calculator and round to the nearest tenth. 80. Sine of 22 degrees. Make sure you're still in degrees if you have to. If you're paranoid, check it. And we get 29.96, which we round to the nearest tenth. The 6 rounds the 9 up to a 10, so the 29 rounds up to a 30 feet. There we go. Kite's 30 feet up in the air. About 3 stories high if you say a story's 10 feet. It's not always true. Depends on the building, but it's kind of the average. Alrighty, that will close out 5.8, which was applications. Did it right, 5.8 at the top? Yes, I did. So that means we have taught all the material for the test, which means the test will be in a week, like we said. So it'll start at 10:14 at 12:01 a.m. and it will finish 12:15 at 11:59 p.m. If you try and start it 2 seconds late, you won't be able to turn it in. You will have to submit your work, your scratch work, 15 minutes of finishing the test. Again, that's assuming it's the MyMathLab format, which I've said I might change, might. If you think you have any questions that someone just asked a question that you're staring at, I'm not going to answer that out loud. What was I saying? I got distracted. If you have any questions, any longer questions that you think you deserve partial credit on, you can email me and say, hey, Mr. Beckner, can you check out question 17? Check out my work. I think I did a good job. I just messed up the answer somewhere, and then I might be able to give you some partial credit. But remember, you have to make that email. And, in the email, just give me a list of, if it's 3 or 4 of them, give me those 3 or 4. Don't say every single question. I'm not going to give you partial credit on every single question in this type of format. Excuse me. There will be a review assignment located in the homework of MyMathLab that will be comparable to the test. I will not make this go for or against your grade, but you should complete it. Fair warning, if I find that almost nobody is doing the reviews and then everybody does bad on the tests, I will start making the reviews mandatory, either as a part of your grade or as a prerequisite assignment to the test. Make it so like you have to get at least like a 50 or a 60 on the review to even take the test. So please do these reviews. They are going to be similar and helpful. All right, so let us move on. Let's see, can I close this one? 5.8. was that. I just don't want to have too many of these open all at once or Word starts crashing. And then I lose things. So I had a spare one open already. So let's do this. We're not going to get very far in this section, obviously, but we do have 10 minutes, so I need to use our 10 minutes. And this is 6.1, verifying trigonometric identities. Center. Move. Left. Get lots and 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 lots of space. Okay. So verifying trig identities. Trig identities are equations that you must make the left and right side match. You will do this by using various trig properties seen in the last chapter. An identity is only verified once the sides match. Example. Sine squared of theta plus cosine squared of theta equals 1, while true is not verified. So if this is a handwritten problem, if this is where you stop, oh, okay, well, yeah, sine squared plus cosine squared is absolutely the one. That's the base Pythagorean identity. But you did not technically show me that it's done. You would have to show the match. So you'd go from this. You'd go from sine squared of theta plus cosine squared of theta equals 1. And then you say, oh, well, sine squared plus cosine squared is 1. So then you just say 1 equals 1. And then you're done. It's only then that you're done. It is only then that you are done. Now your homeworks, they're basically just going to ask you for a couple steps along the way, or maybe what property you would use to simplify things. So it's not the end all be all, unfortunately. So the way I'm going to be doing my examples is, and we are going to do a whole boatload of these so you can see lots of variety and lots of variability and complexity. So while in the homework and maybe in the test, this isn't how things are going to be done exactly, you still need to be able to follow and replicate what I'm doing, because these trig identities are important for using things down the line. When you have a calculus problem, your calculus problem may be in, say, secant squared, and you don't have a formula for secant squared, so you need to turn it into something involving tangent squared, which you might have a formula for. So how do we do this? I just mentioned that it's by doing all the various trig properties we've already seen, as well as some algebra tricks and tips. So here's some basic tips that generally work. First of all, turn everything into sines, and cosines. So if you have a tangent, turn it into sine over cosine. If you have a secant, turn it into 1 over cosine. I'm not saying you have to. I'm saying these are tips that generally work. I'm not saying you have to do any of these things. And I want to have this bolded. Next tip is to use your Pythagorean identities. The fact that sine squared plus cosine squared is equal to 1, or 1 plus tangent squared is secant squared, or 1 plus cotangent squared is cosecant squared. Those 3 things can be helpful. Which are, again, I said them, but I'll write them down. Sine squared of an angle plus cosine squared of an angle is equal to 1. Then the second one is tangent squared plus 1 is equal to secant squared. And the third one is that 1 plus cotangent squared is equal to cosecant squared. You'll notice that very often moving forward, I won't always say cosecant squared of the angle or cosecant squared of theta. I'll just say cosecant squared. Please understand you still have to write those angles. It's just most people tend to skip saying them when you have to write it 50 times. So those were your Pythagorean identities as a fresh reminder. So another thing that is helpful is to factor a GCF out. If you notice that there's a GCF or maybe a difference of squares or a trinomial, that you can use the shortcut method or the AC method or trial and error or the box method or whatever method you've learned. Please understand, I am not here to teach factoring. I will not teach factoring. That's what Pre-Calc 1 was for. You were supposed to have mastered it then. If you have not mastered, go and do 500 of them this semester and master them. Because you will be factoring things that aren't going to just be x squared minus 9. You're going to be factoring things that look like sine squared minus 9. How are we on time? 1/3, okay. Combining fractions sometimes helps if you have separated fractions. Or if you have just one fraction, separating your fractions or splitting fractions may be helpful. Using your even and odd properties of your trig functions. Remember, cosine was even, sine and tangent were odd. Even meant that the negative internal angle can just be deleted. Odd meant that the negative inside just gets dragged outside. So refer to your old notes for that. Something else that can be helpful. When you have separated fractions or maybe even just one fraction, if the bottom has got multiple parts, multiply top and bottom by the conjugate. I can spell, I promise. I just can't type well. Actually, the actual fact there is exactly the opposite of that. I type quite well and spell terribly, but just that word I know how to spell and was just making boo-boos. So by the conjugate, so you should have practiced that technique over and over in Pre-Calc 1 when you had something like 1 over 5 plus 3i, you multiply top and bottom by the conjugate of the bottom, which would have been 3. I don't remember what I said. Let me start over. 1 over 3 plus 5i, its conjugate would be 3 minus 5i. If you just have a fraction equal to a fraction, you could cross multiply. That might be helpful. Maybe one side looks really, really, really difficult and you don't even know where to start. So maybe you just try one side and then both sides eventually. And very often, I know that this is the technique I've probably used more than anything else in the grand scheme of things. Start over. Sometimes you're going to hit a dead end and you just got to start over and use a different technique along the way. Now, it could have been because you made a mistake, which would be unfortunate, but quite often it's just you're not seeing the way to approach. Now, here's the thing about these trigonometric identities. One problem could be done maybe 4 ways, maybe 9 ways, maybe 17 ways, maybe 27 ways, or maybe just 2 ways. There is a lot of variability with these. Some of the examples that you'll see me do next class, you'll see me do them more than once to prove the point that it's not absolutely do this or absolutely do this. And I didn't say that this is any kind of order. It's, okay, yeah, this thing might help you. Maybe another student doesn't like doing it and they manage to just use this middle Pythagorean identity and get away with the problem from there. So I believe that every example I'm going to be giving you has at least one alternative method, several of which I will show an alternative method. Some I won't. Just kind of once we get to the point of, all right, you've seen this enough, we got to do, we can't just spend 5 days on verifying identities. But pencil paper, this is something a lot of people don't like doing because it feels like, oh, it's the perfect storm blend of trigonometry and algebra, and it really is. You've got to know all these little pre-calc things. You've got to know, for pre-calc 1 things that is, you've got to know all your trig. If you're missing a single Pythagorean identity, you might not be able to solve one. I will tell you that my favorites out of this list are turn everything into sine and cosine. I do that 98% of the time for my problems. When you do that, you don't even have to know these other Pythagorean identities because you're only going to see sines and cosines, so you really only have to know that one. Remember that I said you can also, instead of memorizing the second and third, develop it by dividing by sine squared or cosine squared on both sides of the first equation. Factoring, definitely important. Combining fractions isn't necessarily my favorite, but splitting fractions I find can be helpful. And then starting over, those are probably the 4 that I use the most of, but I'm not saying I won't ever do any of these things. You will definitely see me do some of these things, if not all of them. All right, so on that note, we're going to stop there. When we come back next class, we'll display the list for a little bit, but then we will dive right into these. Remember, the test is not during a class. The test is on your own time. We will still hold class a week from today on that Wednesday. We especially, I was going to do that anyways, but especially since we have to make up that day that we lost due to my life. All right, so we'll call it there. Please email me if you have any questions. Have a good one. Work on your homework. I will let you know when the review is up. I will let you know when I have the final details about the test, but the review will be up no later than Monday morning. Again, the review will be up no later than Monday morning. All right, have a good day.